Hello, I'm Serkan Güldal. I'm going to present a paper titled Machine Learning Attempt to Conflict Detection for UAV with System Failure in Use Space. Our method is Recurrent Neural Network RNN. So before that, let me introduce who am I first. So I am an assistant professor in Adıyaman University, and I took 1 year leave from my university for the project called UCP. Currently, I am located in Norway, University of Southeastern Norway, and in this project we are more than 20 people. Just I want to mention my distinct collaborators, Dr. Arntzen and Dr. Shashmas. Of course, you can reach me out for more information about the project. Simply, it is a safe separation in use space environment, and we have a dedicated website for that, so ucp.eu. Also, we have a LinkedIn page. We are sharing latest developments in the project. You can find contacts over there also. And for more about me, I have up-to-date Google Scholar profile and ResearchGate profile. Of course, you can reach me out if you find something interesting. So here is the outline for today's talk. We are going to start with the problem definition. What are we trying to solve with this study? And the simulation efforts, which is basically used for the data collection in this research. And our solution is the recurrent neural network. And we are going to discuss implementation results, and we will conclude with the conclusion slide. So let's start with the problem definition. Let me move myself a bit. A UAV is flying with the control of remote pilot, and there is a UTM controls everything in the airspace, and suddenly communication failure occurs, and pilot lose the connection with the drone to direct it, and the UTM service also lost the communication with the drone for any information exchange, and drone starts to fly unsupervised, and it goes for a while. At this stage, UTM wants to know where will it go next, because there's an ongoing traffic on the background, and any collision or conflict can be disastrous. Only information is available is in that moment is the trajectory of the UAV, and there's no known cause for the failure. And it can be hardware failure, software malfunction, or somebody just hacked the drone in that moment. So to do that, we used blue sky simulators to simulate the action of the drone. Here you see drone is started with communication fail, and drone is this green arrow, and this purple line is the trajectory it will take through that time. This is the unsupervised flight, and this information is available, and drone supposed to be go to the straight, and it starts to lean to left, which is the direction for the urban environment. And this is the blue sky video and simulation. Simply in the blue sky, you can make the ATM simulations for drones, for planes, and it has many nice features to be used. And for our purpose, we are just making the flight so we can get the log file, which will be used in RNN. And during this flight, every 1 second, we are recorded the drone's position. And in this position, we have latitude, longitude information available for us. And this moment is the now, and then we are trying to find prediction about where will it go next. So to do that, we used recurrent neural network. Let me mention a few features of recurrent neural network is differentiate between the other neural network type machine learning algorithms. Recurrent neural networks, in short RNN, use sequential data or time series, which is our use case. In our use case, we have the time series of the log data. of the unsupervised flight. And RNN makes the prediction from the last point. When you have the trained RNN model, it just takes the last point and then tries to predict what is the next time step will be positioned. And also, parameters are shared between the layers of the neural network, which is different from the feed-forward neural network. There are a few terminology, just I want to give this terminology for who doesn't know neural network at all. These are oversimplified explanations. If you really want to learn meaning of these terms, I strongly suggest you to go look for those, and then maybe a little bit coding may help you to understand better. So first term is activation function. Activation function is a function that decides which neuron should be included in this structure. So you can have 5 parameters in your input data, but that doesn't mean every parameter will go through the neural network. And batch size is the other parameter, which is the number of samples propagates through neural network. And epoch number is the training neural network with all data. It's one cycle of training. And hidden layer is the neural network that is between input and output layers. And loss function is the difference between expected outcome and predicted outcome. In other words, it measures how reliable our neural network training is done and prediction is good. Recurrent neuron is specific for recurrent neural network, which is the simplest form of RNN, and recurrent layer is the collection of these recurrent neurons. After this terminology, I just want to introduce the structure which we used. As an activation function, we used linear function, and loss function is the mean squared error. We made many case studies, but we are not presenting every study we have done, just we are presenting the distinct results. So, for example, we changed number of hidden layers in 32, 64 to 156 and 1024. And recurrent layer is changing from 1 to M5. And we have 2 input channels, basically latitude and longitude. And then, of course, we have the prediction of these values, which are the 2 output channels, latitude and longitude. Our epoch number is 1000 and batch size changes as 64 to 156 and all of the data. So if we present in the graphical form, we have the input data, and input data is divided based on the batch size, and our dimension for the input data is the batch size. And steps, and step means is the number of steps in the data. So in other words, n seconds of the simulation. And we have 2 channels for latitude and longitude. Here is the recurrent neural network structure. We have input layers and output layers, and we have recurrent layers. Between those, we have hidden layers, changing number of hidden layers. And model is getting trained from in here, and it's taking input to make the predictions. What will be the next position of the drone? Let's discuss the implementation results. Let me move myself to down there. In here, you see the every case study, and in images, you see the blue lines. Blue line is the trained path for the training, and then red is the prediction. And memory size of the route is changing, like 20% means is the last 20% of the route, and 40% is the last 40%. And if you go to the 100% is the whole route is used for training the RNN and make predictions. And this is the route you have observed in the simulation slide. And every column represents the different size of the memory, and every row represents different parameters. So in this case, we are talking about the batch size, and first row represents the batch size for 64, and the second row is batch size to 156, and the last row uses all the data for batch. And these studies are for 256 hidden layers and 1 recurrent layer. This is for visual observation. Of course, we had loss measurement to measure the reliability of the RNN. So let's talk about how intuitive the results. And for 20% and 40%, you can see it's a straight line, so it doesn't deviate much and then it goes straight. And also I want to mention, like, this red line is longer than this one, but RNN results is completed for 2000 time steps to predict the next position. So basically these red lines are equal, but this is just overlapping. So it goes front and then from this point it goes back, and then it is just overlapping with the other lines and you cannot see the full length of the red line. And when we increase the memory of the trajectory, we are starting to see some deviation, like for 60% it starts to deviate, and then for more trajectory, when we get the full scale of the trajectory in turning to the left, we are starting to get loops, like it's trying to turn left, and so prediction is it's gonna turn left a lot, and then it will go back, and then when it goes there, prediction says it's gonna turn left, so it's gonna make U-turn, and then it starts to make loops. And most like it says it's not going to go further, and then it's going to go back to previous locations. And this is for changing batch size. If you consider the changing number of hidden layers, I'm sorry these figures are smaller than previous ones, but just I want to show the whole view of the experiment. That's all it about, but everything is stays same, and I will explain if you cannot see the numbers. And this is done for batch size is 256, and recurrent number of layer is 1. And number of hidden layers changing as 16, 32, 64, 256, and 1024. So each row represents different number of hidden layers, and each column is same memory of the trajectory. And for 20% and 40% of the memory, we are getting a straight line, no change about that. And when we increase the 80% and 100%, we are starting to get the loops, and for 60%, we are getting a little bit deviation. For the number of hidden layers is 256. And it is interesting, we didn't see for other simulations, and for 80% of data and the 64 number of hidden layers, it's not going to left. So when it comes to here, prediction says it's going to take to right turn. So slightly right turns is taken. We are going to see in the loss measurement, it is not a reliable RNN result. Also, it's not intuitive. But since we are considering a malfunction in the UAV, we may need to consider if there is a heavy traffic on the right side of the UAV. So this is the last visual of the simulations. In here, you see the batch size is 256 and number of hidden layers is 256. But number of recurrent layers is changing as 1, 2, and 5. So 20% and 40% memory again shows the straight line or no line at all, so it just goes back. And when we get to 60%, we are getting a little bit curve here, so which shows deviation in the prediction. When we increase the memory of the trajectory, we are starting to get loops and similar results as the previous ones. If we look at the loss measures, it's basically the quality of RNN. The lower score means is the better RNN, and lowest scores are highlighted with the bold. So let me explain what you see here. Here you see simulation results for batch size 256 and number of recurrent layer is 1, and number of hidden layers are changing 16, 32, 64, 256, and 1024. This part of the table showed for latitude value, and this side of the table showed for longitude value. And each row represents root memory. And let's say for this value is number of hidden layers is 1024, and remember root is 20%, so last 20% of the trajectory is used for RNN. When we look at the table, if short memory for training, we need to use higher hidden layers obtain better RNN results. And when we increase the almost to full scale, we can reduce to 256. And similarly, you can see for 256 and 1024, we are having better results. On the other hand, for 16, 32, and 64, we don't have any good results respect to the other results. So number of hidden layers could be kept high. And this is for changing batch size. Here you see number of hidden layers 256 and number of recurrent layer is 1. And batch size changes 64, 256, and all. When we look at the best scores for the short memory, we are getting best scores in the batch size is 64 and the lowest in the listed batch sizes. So, and when we use the all data, we are getting no best score. So batch size needs to be kept small to get more reliable results. And 256 is the best for 100% of the memory for this use case. And this is the last one. Here you see the batch size is 256 and number of hidden layer is 256, but number of recurrent layers changes as 1, 2, and 5. And here on the table we see if we use portion of the data, we need to use higher number of recurrent layers. But when we use the full scale, like 100% of the trajectory, one recurrent layer is enough for latitude and one recurrent layer is enough for longitude predictions can be said. So that's all about the discussion of the implementations. And last slide is about conclusion. Our conclusions are, first of all, tracked affects the prediction since we can see from the short memory calculations and long memory calculations. And reliability of number of recurrent layers is depend on the training data. So changing training data changes requirement of the number of recurrent layers. And higher number of hidden layers provides a more reliable RNN prediction, and smaller batch size provides a more reliable RNN prediction also. So thank you for your patience and giving your time to listen. If you have any questions, I will be happy to answer. You can reach me out through my email accounts, also the other profiles in available. You can just search my name on Google and then you can find many communication channels to me. Also, if you have any information needed for the project, I would like to be happy to answer, and anybody in the project will be happy to answer also. If you can follow us on the LinkedIn, you can have informed with the latest development of the USAPA project. Again, your time is very, very appreciated.